Okay, hi guys. Today I will try this Zoom actually. Let's see how it will go. So today we will cover this efficient estimator concept. Then we will see the limiting distribution of Mles. Okay, so last time we derived the minimum bound, minimum lower bound, lower bound for the variance of all unbiased unbiased estimators of unknown parameters. So we actually didn't I didn't show you how to find the estimators, and then we just tried start with a sufficient estimator. Using sufficient estimators, we can find this lower bound for the variance, and the variance of an estimator of a sufficient statistic attains this lower bound. We just covered that. But there is an easier way to find it actually, to decide an estimated, unbiased estimated attains this lower bound or not. There is a starting point for this. Okay, so let's start with efficient estimators concept. So efficient estimator is basically better than it's kind of we said that best estimators are minimum variance unbiased estimators, but efficient estimators are minimum variance unbiased estimators. But minimum variance unbiased estimators will not have to actually does not have to take attains the minimum variance property, but efficient estimators has to attain this property. So it's kind of, they are better than, a bit better than minimum variance unbiased estimators actually. Sometimes we don't have an efficient estimator, but we have a minimum variance unbiased estimator. Okay, so let's see how to find an efficient estimator. So Y is an efficient estimator. Actually, okay, start with an N. So it's a unique estimator also. Estimator, I will use this capital EE notation for this, of its expectation. Expectation, let's say it's m theta, function of a parameter. It can be just theta. If its variance reaches the Kramer-Rao lower bound for m theta. Okay. So basically, this means that if a variance of an unbiased estimator of m theta is taking minimum value, okay, then that estimator is the efficient estimator of m theta. Okay. So we need to consider expected y. Expected y should be m theta, and variance of y should equal to Kramer-Rao lower bound for m theta. So if this is the case, y is the efficient estimator of m theta. Okay, so we have two rules. Y should be an unbiased estimator, and its variance should attain the Kramer-Rao lower bound. So there are some properties of efficient estimators. An efficient estimator of m of theta, may not exist. Okay, so it's not always exist. Although we can find minimum variance unbiased estimators, we cannot find efficient estimators all the time. And if it exists, m theta, if exists, it is unique. Okay, so we have only one efficient estimator for an unknown parameter. And if the efficient estimator of m theta exists, then it is the unique minimum variance unbiased estimator of m theta. Okay, so efficient estimators, if they exist, they are equal to minimum variance unbiased estimators, but sometimes we cannot find them, although we can find minimum variance unbiased estimators. Okay, so the rule on the uniqueness or existence, if the minimum variance unbiased estimator of m theta is not efficient estimator of m theta, okay, then the efficient estimator of m theta does not exist. Okay, so if minimum variance unbiased estimator is not efficient estimator, then efficient estimator does not exist. Okay. Okay, so I will skip that. Okay, so if efficient estimator does not exist, we still can find asymptotically efficient estimator of those. Okay, so if let's say y is an asymptotically efficient estimator of m of theta, if in the limit when n goes to infinity, expectation of y goes to m of theta, okay, and limit when n goes to infinity, variance of y equals to Cramer's rho lower bound for m of theta. Okay, so if this is the case, basically limit when n goes to infinity, efficiency equals to 1. Okay, so okay, so there are some other properties. Let's continue with those. So for a random sample, efficient estimator or asymptotically efficient estimator of m of theta is also a consistent estimator of m of theta. Okay, so variance goes to 0 when n goes to infinity, and it's asymptotically unbiased or exactly unbiased estimator. And we have one more thing for a random sample again. Usually we assume we have a random sample. Efficient estimator or asymptotically efficient estimator of m theta is asymptotically normally distributed. Okay, so when we have a y, let's say it's efficient or asymptotically efficient estimator, this is asymptotically for large n, normally distributed with mean m of theta, unbiased estimator or asymptotically unbiased, and the variance equals to Cramer rho lower bound for m of theta, which is the derivative of m theta, take the square, and n times I theta. Okay, so this helps us to find the asymptotic distribution of efficient estimators or asymptotically efficient estimators, and using those basically we can create some hypothesis tests. So this means that basically then y minus m of theta over in square root Cramer rho lower bound for m of theta, okay, so distributed as or we can say actually the limit versus standard normal. Okay, so using this, basically we can create some kind of test based on the value of theta. Okay, so we can test that the expected y equals theta or not, whatever that theta is. Okay, so this helps us a lot. Okay, and another thing that I want to tell you about this is we should start to find efficient estimators using the Mles. Okay, we have to check. Okay, so let me say steps to find efficient estimators of m of theta. So this is a general case. It can be just theta, theta square, whatever the function of m theta is. Okay, step 1. Find the Mle of theta. Sorry, first of all theta by differentiation. Okay, so we cannot use intuition method, order statistics, differentiation. So this is step 1. Okay, then step 2, using the invariance property, find the Mle of m theta. If m theta is just is theta, then you can skip step 2. Okay, so m theta hat. After that, check whether theta hat is an unbiased estimator of, or m theta hat actually, unbiased estimator of m theta. Okay. Step 4. If your answer to step 3 is yes, check variance of m theta. So here we are checking that this one equals to m theta. Okay, we have a question mark here. Then m theta hat equals to Kramer rho lower bound of m theta. Okay, if yes, m theta hat is the efficient estimator of theta. It is also the minimum variance unbiased estimator of m theta. Okay, if your answer to step 3 is no, okay, so we said yes, no here, then the efficient estimator of m of theta does not exist. Okay, in this case, then check asymptotic efficiency. Okay, so this is the steps that you need to follow. Okay, so we start with maximum likelihood estimators. Okay, so let's solve some questions. Then you may understand what we are doing better. Okay, so this is step 2, step 3, step step 4. So we have some yes questions and no questions. We have one yes here. So to know this part actually, if also, let me say, if variance of theta hat also not equal to Kramer rho lower bound theta, then efficient estimator does not exist. Okay, we have also this. Okay. Okay, so let's consider an example. Let's suppose an example. X distributed as Poisson with parameter mu. And you know the PMF, you should know Poisson PMF. We have lots of examples that follows the Poisson in real life. Okay, so start with finding the Kramer rollover bound for mu. Actually, we found this, but let's found it again. Then you may remember how to calculate it. Okay, so first of all, we need to find the Fisher information. You know the meaning, okay, of the Fisher information, what we measure. Okay, so this is just log PMF in this case. So it is minus mu plus x ln mu plus ln x factorial. Okay, so I'll take the derivative of lambda with respect to mu. So we have minus 1 plus x over mu. Okay, this is our score function, if you remember. So how close our estimator to the parameters can be measured by this function. So the expectation of this should be 0. And as you can see, basically we have 1 plus expected x, which is expected x, over mu. Expected x is just. So this is 0. Okay, so first checkpoint is done. Then the second derivative with respect. Okay, then we have minus x over mu square. Then the information about mu is minus expectation of the second derivative of how steep our PDF can be measured by this. So we have minus expectation minus x over mu square. Okay, so expected x over mu square. So mu over mu square, we have 1 over mu. So this is the Kramer rollover bound. Okay. Okay, so we already found okay, so let's repeat that. Find the Kramer rollover bound for e to the minus mu. Okay, so all you need to do is take the derivative of e to the minus mu with respect to mu, then take the square and then replace n times I mu here. Okay, so we have mu e to the minus 2 mu over n. Okay, so this is the Kramer rollover bound for the for e to the minus mu. Okay, so find the efficient estimator of theta if it exists. Okay, so we start with Mles. Okay, step 1, find the Mles of theta. Actually, we know the Mles of theta, but let's find it Okay, so find the likelihood function e to the minus n mu to the summation xi over xi factorial. So then take the log likelihood to ease the calculations, and mu plus summation xi ln mu minus summation ln xi factorial. Then take the derivative of the log likelihood function with respect to mu. We have minus n plus summation xi over mu. Equate this to 0 to find the maximum point of the likelihood function. Then we obtain mu hat as x bar. Okay. Then check also the second derivative, which we have a concave down shape to make sure that uh, d mu squared, where mu equals mu hat, it should be negative. If you do the calculations, you will see that it's negative. Okay, then this is our MAD. Check its expectation. Okay, so let's check expected theta hat. Not theta hat in this case, mu. Sorry, mu hat. So expected x bar. So expected x bar equals to expected x, and it equals to mu. So great. Our MAD is a unbiased estimator of mu. Then check its variance. So variance of mu hat equals variance of x over n, and which is mu over n. What was our Kramer rollover bound? Oh, we only, sorry, I only find the Fisher information here. Let me continue. So the Kramer lower bound for mu will be 1 over n times I mu, which is mu over n. Okay, so my Kramer lower bound exactly equals to the variance of mu hat. Okay, so this is done also. So this means that by definition, mu hat, which is x bar, is the efficient estimator of mu. Also, this tells us that x bar is the minimum variance unbiased estimator of mu. Okay. We have one more part, but actually this is not exactly related with the Kramer rollover bound or efficiency, but let's solve that also. So show that n minus 1 over n to the summation xi, I from 1 to n, is an unbiased estimator of e to the minus mu. Okay, so we know that x distributed as Poisson with mu, so this means that for a random sample, summation xi also distributed as Poisson, but in this case our parameter is n times mu. So we already know that we have to find the distribution of summation xi because we need to take the expectation of this function based on the random variable that we have, which is the summation xi. Okay, so expectation of n minus 1 over n to the summation xi. Let me erase this. Okay, so we need to find this expectation. So let's write the function itself that we want to find. Okay. Actually, we can replace it by y. Maybe the notations will be more easily to understand. Okay, summation xi over summation xi factorial. This type. I from 1 to n. So we need to find this expectation. So if you have such a thing, basically you have to combine the things with summation xi. So this is our main random variable. Okay, so let's do that. Okay, so we have a sum, I from 1 to n, e to the n mu. Okay, so when we combine that, so we have one n term here. Okay, so one n term here. So these will cancel out and we will have n minus 1 times mu okay, to the summation xi, and then again summation xi whole factorial. So this looks like exactly the Poisson PDF, but instead of n times mu in this case, we have n minus 1 to the mu. If we put one term here outside, or when we add and subtract 1 here, mu actually, add and subtract e to the minus mu, e to the mu, then we'll have exact Poisson PDF. Okay, so let's write minus mu out from 1 to n. So then we will have exactly this one. Okay, so plus mu part is here, minus goes out, and then we have n minus mu, n minus 1 mu, yeah, summation xi and summation xi factorial. So this will be the PMF of Poisson, but now the parameter is n minus 1 times mu, then from the whole range, so this will be, this is not n, it goes to infinity, sorry about that, I have to change. Okay, so upper bound for Poisson, so it is 1. So at the end we ended up with e to the minus mu. So we showed that n minus 1 over n to the summation xi, the non-biased estimator of e to the minus mu. Okay, so n minus 1 over n summation xi is an unbiased estimator of e to the minus mu. Okay. Okay, so let's consider another example. I already solved this. Oh, okay. Okay, I already told you that Kramer rollover bound does not work where the range of x depends on theta. Okay, so you cannot find efficient estimators for those cases. You cannot find minimum variance unbiased estimators using Kramer rollover bound approach. Also, you cannot find minimum variance unbiased estimators when the range of x depends on theta case using exponential class, so you have to use the definition. Okay, so find sufficient estimator using factorization theorem, and then you have to show that that estimator, sufficient estimator, is a complete statistic also. Then you have to use the Lemma-Scheffer theorem. Okay, so let's consider another example. So we have a negative exponential distribution here, 1 over theta. Okay, so here the PDF is theta e to the minus x theta. X is positive, theta is positive, so this is a negative exponential. As you can see, the range of x not depend on theta. So we can use Kramer rollover bound approach here. Okay, so if you remember here, we already solved this question to be able to find minimum variance unbiased estimator of theta. Okay, so what we find before, using the exponential class, we find that y equals summation xi is a complete sufficient statistic for theta. We already showed these if you look at your previous notes. And n minus 1 over y is the minimum variance unbiased estimator of theta. So we already found that. What we mean by that actually, so we found that expected n minus 1 over y equals to theta, so it's an unbiased estimator, and we already found that the variance of this quantity equals to theta squared over n minus 2, where n should be greater than 2, so that the variance exists. So here y distributed as gamma distributed, if you remember, and using that we can calculate expectation and variance. Okay, so let's find the Kramer rollover bound for theta, and let's check this variance attains the Kramer rollover bound. Okay. Okay, so let's find Kramer rho lower bound for theta. Okay, so start with finding lambda, which is the ln of the PDF. So we have ln theta minus x theta. Find the score function by taking derivative of the lambda with respect to theta. So we have 1 over theta minus x. Here, this is a score function. You can check your calculations here as everything it goes nice or not. We all have 1 over theta minus expected x. This is negative exponential, so expectation is 1 over theta. So this is 0. Checkpoint down. Take the second derivative to find how steep our PDF is, the variation. We have a steep one or slowly increasing PDF. Okay, so take the derivative of lambda prime with respect to theta. So we have 1 over theta squared. Then our Fisher information will be minus e to the second derivative. If you use this formula, it's easier. As you can see, you don't have to take any expectation. We don't have any x term actually. So it's just constant 1 over theta square. Then the Kramer rho lower bound for theta will be 1 over n times. Why did I write mu? It should be theta, sorry about that. So I have theta square over n. Okay, I have theta square over n. I have theta square over n over, oops, sorry. N minus 2 here. I have this. So these are not equal to each other. So this means that since or because variance of n minus 1 over y not equals to Kramer rho lower bound for theta. Okay. This quantity n minus 1 over y is not the efficient estimator of theta. And this actually tells us that efficient estimator of theta does not exist here. Okay, we don't have, because this is the minimum variance unbiased estimator n minus 1 over y. Its variance does not attain the Kramer rho lower bound. Okay, so we don't have an efficient estimator here. Okay, so we have the minimum variance unbiased estimator. If minimum variance unbiased estimator exists, then we can say that maybe when we have an efficient estimator, basically I have to say, we can say that it is minimum variance unbiased estimator, but we cannot say the reverse. Okay. Okay, so let's check. We can say asymptotic efficiency here. Okay, so we already showed that expectation of n minus 1 over y equals to theta. So here we have unbiased estimator. Let's check its variance. So variance n minus 1 over y is theta squared over n minus 2. So when n is too big, so asymptotically we can say that for large n, this actually equivalent to theta squared over n, which is the Kramer rho lower bound for theta. Okay, so this means that we can say that n minus 1 over y is an asymptotically efficient estimator of theta. Okay, and then we can also find the asymptotic distribution of this. Then we can find an asymptotic distribution of n minus 1 over y. This is y. Okay, so our statistic is n minus 1 over y, and we know that it is asymptotically for large n, normally distributed with mean theta, and variance equals to Kramer rho lower bound for theta, which is theta squared over n. Okay, and if you can see, actually this is also a consistent estimator. because it's unbiased, and when n goes to infinity, its variance goes to 0. Okay, it's also a consistent estimator of theta. Okay, so unbiased estimator of theta, and variance goes to 0 as n goes to infinity. Okay. Also, we can also calculate the efficiency here if you want. So when we consider efficiency of theta, calculate this. Okay, so we have Kramer rho lower bound for theta over the variance of n minus 1 over y, which is theta squared over n, theta squared over n minus 2. Okay, so we have n minus 2 over n not equal to 1. Okay, so from here we can see also it's not efficient estimator. Okay, so if this efficiency equals to 1, then n minus 1 over y will be an efficient estimator, but here we can say that it's not. But when n goes to infinity, efficiency of this one goes to 1. Okay, so from here we can also say that asymptotically efficient estimator of theta. Okay. Okay, so we finished that. Okay. Okay, so we have also structural form. Usually we don't use this that much actually, but I want to give you this also. Sometimes just writing our likelihood function or taking the derivative of the likelihood function, we can find the minimum variance unbiased estimators or efficient estimators easily. Or here actually minimum variance unbiased estimators. If derivative of log likelihood function can be written as k times theta, any function of theta times theta hat minus theta. Okay, so here we assume that k theta not equal to 0. Okay, so here where k theta is free from any x terms, it's just a function of parameter, then automatically theta hat is an unbiased estimator of theta, and theta hat is the minimum variance unbiased estimator of theta. Okay, and also this k squared term should relate with the variance. Also, variance of theta hat equals to 1 over k theta. Okay, so if we can write it this way, then we can automatically find the minimum variance unbiased estimator. Okay, so if you can write derivative of log likelihood function in this form, okay, so without using the Lemma-Sheffer theorem, without finding complete sufficient statistics, or without finding the Kramer rollover bound, we can directly find the minimum variance unbiased estimator of theta here. It could be any function of theta actually, so we can replace this theta hat by m theta hat and this theta by m theta, and then this k can be replaced by m theta also in this case. Okay, so let's take the expectation of this derivative. Okay, so this is k times theta times expectation of theta hat minus theta. So in this case, basically, this will be 0 because we assume that expected theta hat is theta. Okay, so it's unbiased estimator. When we take the square both sides, when we take the square or square both sides, basically we can obtain the variance because expectation is 0. So expectation of d ln l theta d theta, take the square, so we will have k theta whole square, then expectation of theta hat minus theta square. So this will all directly relate with the variance of theta hat. Okay, so we have why we have minus sign here. Okay, so this is all related with the with this term. Okay. So this is also related with the minus expectation of d square ln ln l theta over d theta square. Okay, whole square and variance of theta hat. Taking the square of these terms, we have a minus theta term here. Okay. 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 Okay, so then differentiating theta, basically you can see how do we get this minus sign, ln theta, d theta squared. So we have this term times theta hat minus theta minus k theta. Okay, then take minus expectation, so d squared ln theta over d theta whole square equals k prime theta, expectation of theta hat minus theta minus k theta we have. So this is 0 because it's unbiased estimator, and this directly equals to sorry, we have a minus sign here, we have a plus sign here, k theta. Okay. Okay. So from here, basically, we can say that we have k theta square, variance of theta hat. So variance of theta hat equals to k theta. So where this structure form comes here like that, then basically if we can show that when we take the derivative of the log likelihood function. Okay, so if we can write this as this term, okay, then this will be the minimum variance unbiased estimator of theta. Okay, so let's see, can we do it for an exponential? Okay, so let's say we have an exponential distributed random variable. Okay, so let's find the likelihood function. Okay, so likelihood function is theta to the n. Oops, 1 over theta, sorry. 1 over theta to the n e to the minus summation xi over theta. Xi's are positive, theta positive. Here from our previous calculations, we already calculated that theta hat equals to x bar. Okay, so we already know that. So let's find log likelihood here. Minus n ln theta minus, okay, so let me write summation xi as a function of theta hat. So it is n times x bar over theta. Okay. Okay. Then take the derivative of this with respect to theta. Okay, so let's see, we have minus n theta plus n x bar theta square. Okay, so let's see, can we write everything in this form, in structural form? Okay, so we need to write this as x bar minus theta. Okay, so how can we do that? Okay, so let's take an n parenthesis here, and actually, yeah, here it's easily done. So this will be the variance of x bar, as you can see, 1 over. Okay, so it is our k theta, k of theta. So we can write this in the structural form. It is in the structural form. Okay, so this means that x bar is the minimum variance unbiased estimator of theta. Okay, so this is another thing. If you can realize your PDFs can be written in this form, then you can easily write it. For example, for negative exponential, after some calculations, we can show it this way. So our, oh, this is not negative exponential. Sorry, this is another PDF. Sorry. I think this is, oh, it's beta PDF. Is it beta? No, it's Bernoulli. X Bernoulli theta. Okay, so f of x theta, theta to the x, 1 minus theta to the 1 minus x. X takes value 0 and 1, and theta is in 0, 1 band. Okay, so let's find the likelihood function. So theta to the summation xi, 1 minus theta to the n minus summation xi. Xi takes 0, 1 again. Okay, so find the log likelihood. Okay, so if you combine things with summation xi, it would be easier. Let's see. Okay, so let me keep it this way. Okay, here again, I'm writing this summation xi and n times x bar here, because if you remember, our Mles was x bar for Bernoulli. Okay, and then our log likelihood will be n x bar ln theta plus n minus nx bar ln 1 minus theta. Let's take the derivative. Okay, so nx bar over theta minus n minus nx bar over 1 minus theta. Okay, so now let's try to write this as, can we write it as k times theta, theta is x bar minus theta. Let's see, can we write it this way or not? Okay, so let's put the question marks. Okay, so we need to do some little calculations and keep x bar and theta in one side. Okay, so let's equate the denominators. So we have n x bar 1 minus theta minus n minus nx bar theta. Okay, so when we do that, we have, okay, so let me open this up. N x bar minus n x bar theta minus n theta plus n x bar theta. Okay, so there should be some parts. Yes, this and this cancels out. Then I have n theta 1 minus theta x bar minus theta. Yeah, I could write it. So this is my Mles. Okay, and then this will be r k theta, which is 1 over variance of x bar. Okay, Then, since I can write my PDF, actually log likelihood, derivative of log likelihood in a structural form, this means that x bar is the minimum variance unbiased estimator of theta. So this is another way to find minimum variance unbiased estimators using the structural form. So it is in the, but it's not always easy to find, easy to write our derivative of log likelihood function in this form. If you can write it, you are lucky to find minimum variance unbiased estimators. You might try actually to use this, or just use exponential class approach or definitions or Kramer lower bound approach. Okay, so this is another way to find the minimum variance unbiased estimators. Okay, so let's talk about the limiting distribution of Mles. Let's solve some questions related to that. Combine everything with efficiency and the limiting distributions. And we will finish the class. Okay, so limiting distribution of Mles. Okay, so here, start with this. Find theta hat, Mle of theta. But this Mle has to be obtained by differentiation method, not intuition. Okay, so if the range of x depends on theta, we cannot use this approach. Again, let's assume that we have a random sample of size n. Okay, then by using the invariance property, we can find the Mle of m theta hat easily. So I will give you the general form of the limiting distribution of Mles. So Mles have good large sample properties actually. So because of that, we prefer to use Mles to represent the unknown parameters. So we can easily find them, and they have good properties, like even though they not exactly attains the minimum variance, the when n goes to infinity, variance goes to zero. So they are usually consistent estimators, and we can find their asymptotic distribution when n goes to infinity, or when we have a large sample sizes. So this is a good property. So then we can find the confidence intervals, do hypothesis testing, any type of calculations or modeling can be done using the Mles. Okay, so then we can find the limiting distribution of m theta hat. Basically, these are related with the efficiency, also Mles. Then we can find their distributions using the asymptotic distribution of efficient estimators. So this is for large n. So here n does not go to infinity. Okay, so the variance term can be a function of n, actually, the sample size. And the Kramer rho lower bound for m theta. Okay, so it is the m prime theta whole square divided by n times I theta Fisher information. Okay, and from here we can easily find the asymptotic distribution of the Mle of theta. Again, this is asymptotically for large n normal with theta, and Kramer rho lower bound for theta. Whatever the estimator is or the parameter is, we are finding Kramer lower bound for that parameter, 1 over n I theta. Okay, so from here we can standardize it. Okay, then write 1 over n times I theta in square root. So n times I theta theta hat minus theta converges to standard normal when n goes to infinity. Okay. And when we have more than one parameters, basically we will not use more than one parameter case, but we can easily use these for more than one parameters cases, and all of those will be asymptotically normally distributed in this case. But here, to be able to find the Fisher information, we will have a Fisher information matrix. Okay, so using the diagonals of this matrix, we can find the variances of each theta hat or m theta hats. So I will skip that part. Okay. Okay, so we have some rules again. So efficient estimator of m theta, let's say m theta hat. It is a function of a sufficient statistic for theta. Okay, and we have a linear functions if y is the efficient estimator of m of theta, then when we consider z equals a plus b y, this is also the efficient estimator of a plus b m of theta, where a and b are constants. Okay, so let's consider normal example here, only one parameter case. So in undergraduate level, one parameter case is enough, I think. As known here, sigma square is known, and let's say we have a random sample of size n. Okay, first of all, let's find efficient information. Find I mu. Okay. Okay, so first of all, find the log PDF. So you know the normal PDF, you have to know as a statistician. 1/2. Sigma square is known, so I can keep sigma square in here as a constant, minus x minus mu whole square divided by 2 sigma square. Take the derivative of log PDF with respect to mu, find the score function. So it will be 2 times x minus mu over 2 sigma square. This is the score function, so checkpoint for us. And as you can see, expected x minus mu over sigma square will be 0. Expected x is mu, so this is done. Oops, it's here. Okay, so take the second derivative. Okay, so we have minus 1 over sigma square, right? Okay, then the Fisher information will be minus second derivative here, 1 over sigma square, and then Cramer rule lower bound for mu will be 1 over I mu, which is sigma square over n. Okay. Then let's find the Fisher information. Fisher, not Fisher information, the efficient estimate. Okay, sorry. Of mu, if it exists, so we need to add this, it might not exist. Okay, so our starting point here is finding the Mle of, so step 1, find the Mle of mu. So for normal, we already know that Mle is x bar. Okay, then in step 2, check the variance of mu hat. Because we have just mu, we skip this step 2 that I wrote before for m theta case. So it is sigma square over n. And then check whether this equals to Kramer rho lower bound for mu, which is sigma square over n. We already found that. So this is good. This means that actually our mu hat, which is x bar, is the efficient estimator of mu. Actually, the question is that, but we can also find the asymptotic distribution of x bar. So x bar distributed as asymptotically large and normal with mean mu and variance sigma square over n. Actually, this is its exact distribution because we started with normal. You know that x bar always distributed as normal. So this is true for any n actually. Okay, and we already showed that x bar also the minimum variance unbiased estimator. Minimum variance unbiased estimator of mu because it's efficient. Okay, so let's find an efficient estimator of mu square if it exists. Okay, so here let's find the MLE of mu hat square. Okay, by using invariance property, it is just x bar square. Okay, then let's try to find its expectation, and then if its expectation equals to mu square or not. Okay, so this is our first step. After second step, actually, so mu hat square expected x bar square. So it is variance of x bar plus expected x bar whole square. So we have sigma square over n plus mu square. So it does not equal to mu square because mu hat square is not an unbiased estimator of mu square. The efficient estimator of mu square does not exist. Okay, so we don't have efficient estimator here. But let's check it is asymptotically efficient or not. Okay, so here from here we can say that mu hat square for large n equals to mu square. So it's asymptotically unbiased estimator. Okay. Or x bar square is an asymptotically efficient estimator of mu square. Okay. And then when we check its variance, okay. We don't have to check the variance. So we can say that automatically x bar square is an asymptotically efficient estimator. Oh, here I should say unbiased. Sorry. X bar square is an asymptotically efficient estimator of mu square. Then we can find this asymptotic distribution. Large and normal with mean mu square. And when it's directly equals to Cramer law, lower bound for mu square, you don't have to check it when we have a large n actually. So it is so we need to take the derivative of mu square and then take the square of that one. So derivative of mu square is 2 mu. Take the square, so we have 4 mu squares over the Fisher information, which is n over sigma square. So this part equals to 4 mu square sigma square over n. Am I right? Yes. Okay, so this is the asymptotic variance of mu hat square, x bar square, sorry. Okay. Okay, so let's solve one more question for normal when this time mu is known case. So mu is known. Okay, so first of all, let's find the Fisher information for sigma square. Okay. Okay, so this time let's write the LM PDF. So 1 over 2 and then 2 pi. This time separate 2 pi and sigma square because this time sigma square is unknown parameters. So we have x minus mu whole square divided by 2 sigma square. Take the derivative of this for sigma square. So we have 1 over 2 sigma square plus x minus mu whole square divided by 2 sigma to the 4. At this point, you can show the derivative of this, and expectation is 0. The score function's expectation. Take the second derivative. Okay, so it is minus. Oops, take the second derivative. I skipped to the Fisher information part, sorry. Okay, so take the expectation, the second derivative of this will be, let's see, so we have 1 over 2 sigma to the 4, okay, and we have minus x minus mu whole square to the sigma square to the 6, okay, and then the Fisher's information is minus expectation of sigma square. Okay. So our expectation of x minus mu whole square term, so this term will be sigma square. So we have 1 over 2 sigma. Okay, so let me write it. Okay, so it is minus expectation of 1 over 2 sigma to the 4 minus x minus mu. So write capital letters inside of the expectation. Don't forget that one. In the final exam, if you don't write it this way, you will lose 1 point for each of your mistakes. If you don't write the range for a PDF, you will lose also 1 point. Okay, so be careful about that. Okay, so it will be 2 sigma to the 4. This is sigma. Okay. Okay, so this is efficient information. Then let's find an efficient estimator of sigma square if it exists. Okay, so at this point we need to check the expectation of the Emily. Okay, so find Emily of sigma square. So we previously found that, remember, it is summation xi minus mu whole square divided by n. Okay, so when we take the expectation of sigma hat squared, it is sigma squared. Okay, so everything is nice, good. And then when we take the variance of this, we will have 2 sigma to the 4 over n. You have to use the properties of chi-square distribution here. So it exactly equals to the Kramer-Rao lower bound for sigma square. So this means that our MLE here is the efficient estimator of sigma square. It's also the minimum variance unbiased estimator. Okay, we can also talk about its asymptotic distribution. Normal with sigma square and variance equals to Kramer-Rao lower bound. Okay. When we consider efficient estimator of sigma, okay, so let's find the MLE of sigma. So we will get this one. And when we take the expectation of sigma hat, it's not sigma actually. So when you calculate, you will see that. So here you need to use the chi-square distribution again. So here efficient estimator for sigma hat does not exist. Oops, I should say. First of all, it is not the efficient estimator of sigma. So this means that efficient estimator of sigma does not exist. Okay. Okay, but we can find an we can find an asymptotic distribution. First of all, we need to show that sigma hat is an asymptotically efficient unbiased estimator of sigma. Okay, so first of all, we need to show that, and then from that we can, not square, sorry, asymptotically for large and normal with sigma, and then you have to find the Kramer-Rao lower bound for sigma. So here you have to think that sigma square as a whole parameter, then you can find this as sigma square over 2n. Okay, so when you calculate, you will see that. Okay, okay, so we already solved this question. This is very similar to the previous one. Okay, so let me okay, so this is very similar to the previous one, but let me solve this question also. Exponential question actually. So this is the case when we have exponential theta square. So our parameter is theta square here. So f of x theta is 1 over theta square e to the minus x over theta square. Okay. Okay. So here's the expected x equals theta square and variance of x equals theta to the 4. Okay. So let's find the Fisher information for theta. Okay, Fisher information in a random variable. So let's find the log PDF here. Okay, this is a log PDF. Find the score function. Okay, so when you take the expectation of this, you will see it's an unbiased estimator. So this is a check, it's 0 actually. Score expectation of score function. Expected x is theta square. So you will see this. Why we have n? I don't have an n here. Sorry about that. There should be no n term. Okay. Okay, then take the second derivative. So 2 over theta square plus I have 6x over theta to the 4, right? Okay, yes. Then our Fisher information will be minus expectation of the. So I have 2 minus 2 theta square. Let me check. This should be a negative sign. Sorry. Our Fisher information should be always positive. Plus 6 expected x over theta to the 4. So Fisher information will be 4 over theta square. It's positive. So be careful. Okay, so it should be positive. If you get negative, then you made something here wrong. Okay, be careful. Okay, so B, find the efficient estimator of theta square if it exists. So here, as you can, if you do the calculations, you will see that Mle of theta will be this one. So the Mle of square will be x bar, okay? Then expected x bar, here expected mu, expected x, it is exactly the same, and variance of x bar equals for variance theta to the 4 over n. Okay, so let's find Cramer rollover bond. Let's check the Cramer rollover bond equals to the variance of x bar or not. So Cramer rollover bond for theta squared. So I have 2 theta, take the square, and n times I theta for theta squared over n. Where is Fisher information? Okay, so I have 4 over theta squared. So theta to the 4 over n. Yeah, they are exactly the same. So this means that x bar is the efficient estimated of theta square. It's also the minimum variance unbiased estimated. We can find this asymptotic distribution. This is not the question, but you can also find the asymptotic distribution for large n normal with theta square and variance equals to theta to the 4 over n. Okay, an extra thing. Okay, so let's find an efficient estimator of theta to the 4. So the question is like that. It's a bit long. Find the efficient estimator of theta to the 4 if it exists. Okay, and if it does not exist, find an asymptotically efficient estimator of theta to the 4 and specify its asymptotic distribution. Okay, so the question is this. So first of all, let's find the MD of theta to the 4. So here we need to use the asymptotic invariance property. So it's x bar square. Right, okay. Let's check the expectation of x bar square. So it is variance of x bar plus expected x bar whole square. So we have theta to the 4 over n plus theta to the 4 equals n plus 1 over n theta to the 4. So it's not equal to, let me check. Oh, okay, it's not an unbiased estimator of theta to the 4. So this means that x bar squared is not an unbiased estimator of theta to the 4. So this means that efficient estimator of theta to the 4 does not exist. Okay. But as you can see, expected x bar whole square for large n equals to theta to the 4. So this means that x bar square is an asymptotically unbiased estimator of theta to the 4. Okay, so this means that x bar square is an asymptotically efficient estimator of theta to the 4. Then we can find its asymptotic distribution for large n, normal with theta to the 4, and variance equals to Cramer rule lower bound for theta to the 4. So take the derivative of theta to the 4 and then take the square of that one. So we have 4 theta cube. Let me see. Yeah, 4 theta cube. Okay, so take this square and times what was our Fisher information? Theta 4 over n over theta to the 4. Oh, this is not, sorry. Oops. Where's my Fisher information? 4 over theta square, okay, 4 over theta square. 6, 8. Okay, then I have these 4 and 4 cancelled out. We have 4 theta to the 8 over n. Okay. It's also consistent estimated. As you can see, it's unbiased, asymptotically unbiased for theta to the 4, and variance goes to 0 when n goes to infinity. It's also consistent estimator of theta to the 4. Okay, one more part for this. Find the minimum variance unbiased estimator of theta to the 4 if it exists. So we couldn't find efficient estimator, but we can still find the minimum variance unbiased estimator. Let's see. Okay, so here, first of all, we need to find a complete sufficient statistic, and then find the unbiased estimator of theta to the 4 with respect to that complete sufficient statistic. So let's write our PDF in an exponential class form. So we have e to the minus 2 ln theta minus x over theta squared. X positive, so here it does not depend on theta. The range of theta is an interval. And we have p theta term, which is minus 1 over theta squared kx is just x, and p theta equals -2 ln theta, and we have sx which is 0 here. So here basically our PDF is a member of the exponential class of PDFs of continuous type. Okay, so here the range of x does not depend on theta, so we assume that you can check the conditions, regularity conditions. We have a regular case, exponential class. We assume that we have a random sample of size n, so this means that summation of k function, which is summation of xi, is a complete sufficient statistics for theta. Okay. After that, we need to find an unbiased estimator for theta to the 4. Here, we know that from part C, we know that expected x bar square equals to n plus 1 over n theta to the 4. Right? Let's look at part C. We already found this expectation. Okay? So from part C. Okay, so it's not unbiased, but we can find an unbiased estimator easily by just multiplying both sides by n over n plus 1. So by Lehmann-Schiffer theorem, n over n plus 1 x bar squared is the minimum variance unbiased estimator of theta to the 4. Although efficient estimator of theta to the 4 does not exist, we still find minimum variance unbiased estimator for theta to the 4 using consistent complete sufficient statistics and finding an unbiased estimator of an unknown parameter with respect to this complete sufficient statistic. Okay, I will stop here. So if you have any questions during the class time, you can ask. See you in class, okay? So let me go back to the Zoom.